Hello, I'm Susan Nash, and I'm thrilled today that we have Dr. Stephen Tedesco with us, who has published a very influential text on helium, published by Elsevier. And in addition, he's working on a second edition. And we're really fortunate to have him today to comment on some of the situations with the helium supply in the global situation today. So welcome, Steve.
Well, thank you very much, and I appreciate the opportunity to do this podcast. And so I'll get started to share my screen.
Great.
Let's go.
It's just a little bit slow. There's a little bit of lag.
Yeah. So
Okay,
today
now just now click on the presentation mode.
it is on the presentation.
Now it is. Okay, good.
Yeah. So we're going to talk about the helium industry today and where it stands with the recent uh, problem with the Iranian war, as called by some, or the Iranian action by others. Regardless, the helium industry has been severely affected, and it's not really momentary, by the Iranian war. The main facility that Qatar has to produce 20% of the world's helium are basically shut down for several months to maybe a couple of years. In the process, the largest gas field, which produces the helium, has also been damaged. But let's talk about what helium, how that affects us. And we use it in several things, as you can see. Cryogenics creates an inert atmosphere for silicon and germanium crystals. It was actually used extensively in the launch of the Artemis rocket yesterday. Helium is used very much there. Helium use in the U.S. and several other countries is like 25% of their military budget. It's used in welding, leak detection. It's a very inert element, and because of its inertness, it's very, very useful in multiple situations. And then finally, it's really good with party balloons. So that's what everybody remembers. So without helium, there would be no MRIs, no computers present day. So our society would be basically back in the 1960s or 50s. So it's very critical to society, and it's going to continue to grow. It's being used also for AI facilities. It's just a wonderful little element, and it doesn't react with anything. It's very simple. It's got two protons with 1 to 2 neutrons. There's two isotopes that are very important. Helium-3 is used for fusion. Helium-4 is more of the common isotope, and we see that uh, by 1,000 times more than helium-3. Helium-3 is generally generated by nuclear industry, and especially the Soviets and the Russian. Certain reactors generate helium-3, which is very expensive. Other reactors are starting to come on board, like in Romania, China, that will generate helium-3. It's got the lowest boiling point. It's the second smallest molecule, but it's completely inert, non-reactive. It can make a couple of compounds, but it's at pressures and temperatures that you do not see on Earth.
Okay, so I'm going to jump in here though.
Sure,
So
jump in.
helium is H2. So why H3 and why not just fuse hydrogen atoms and create
Helium is
H2?
He. Hydrogen is H2.
Oh,
So H2 is with water,
oh,
and
that's right.
hydrogen, right, it's okay. Hydrogen is very reactive, and so that's why it won't work. It also likes to blow up with the right amount of at 500 degrees, which can be achieved in a lightning blast and that sort of thing. So if you drive a hydrogen car, unless you have a spark, you'll be fine. And many people fear hydrogen cars because of that, but it's really not as much of a concern as, let's say, a lithium battery in a Tesla. They're getting better, but those do like to blow up and burn. But
Okay, but just jumping in here again.
sure,
Hydrogen is H1. It's the hydrogen molecule together that's H2, and it's two
right. But H1 is not very common. They always bond into H2.
right, but I'm just saying, can't you split or do something with hydrogen and turn it into helium? I guess
No,
that's what.
helium is derived from uranium and thorium.
Right, right. Okay, never mind. I was just
Oh,
going
that's
through
okay.
this fanciful
That's okay. Well, I was going to
sci-fi.
get to this anyway. That's okay. But it's good questions. So,
Well, I think it's your fault because you talked about the nuclear reactions causing the
Okay,
reactors.
I'll accept responsibility. Um, this screen is showing helium reserves and production. Basically, there's about 5 countries that produce 80 to 90% of the helium. And then there's dozens of small accumulations, specifically in Canada and US. Actually, Canada is now about 5.5% of the world's helium. South Africa's coming on. They have one nice area. But for the most part, the rest of the world is devoid of helium. And it's not um, that it isn't there, but like in South America, most of Africa, they don't go looking for it. We're finding more and more with the recent exploration, let's say in the past 10 years, we're finding helium in more and more odd places. The hydrogen industry that's popped up seems to have, when they have pure hydrogen with very little else, the helium will be present, and it can be present up to over 30%. The problem with those deposits is hydrogen and helium together the reservoir seems to have extremely low pressures where it does not flow to the surface. It has to be extracted, but the amount is not, it's almost negligible. So that's the problem for the hydrogen industry right now, is that they can't get flow rates to where it would be necessary to replace natural gas. But that's a subject for another time. But anyway, so the US has been the major producer of helium for decades, and it's only in the 60s and 70s did we start seeing it come from elsewhere.
And there are no substitutes for it, no proxies, no
No, there's
substitute.
no, well, you can use other noble gases like argon and
Hmm.
no nitrogen to do welding, but the welds are not, they're very imperfect compared to with helium. Um, so the amount of helium in the atmosphere is 5.2 to 5.6 ppm. It's very constant. It takes 1 billion years plus to generate a single molecule of helium. A lot of the helium we're mining or extracting today was probably put into the earth when it was formed. What is it, 4 or 5 billion years ago? And the helium atom and the hydrogen atom migrate very rapidly relative to everything else up the geologic column and into the atmosphere and out. There are some big problems with helium supply estimations because we keep seemingly finding more and more helium now that we're aggressively looking for it. But regardless, and also a lot of helium has left the planet, so there's got to be more in the Earth's core and the crust and the mantle than we really know about. There's probably a lot of more uranium and thorium in the Earth's crust that's generating helium as well than we can estimate.
Wasn't that one of the attractive aspects of the moon is helium?
Yes. So one of the thoughts is, and there was a movie by Sam Rockwell, I think it's called The Moon, where they're mining helium from the regolith, the upper 2 or 3, 4 or 5 inches. So the solar winds plaster the moon and deposit helium-3 all across it. Helium is the second most abundant element in the universe, supposedly, and hydrogen's the first. But the moon has just collected a lot of helium-3. There's been one company that signed an agreement to deliver helium-3 from the moon about 2.5 years from now to another company. Whether they are able to achieve it or not is unlikely, but the interest in the moon is pretty great. The second difficulty is how do you get it back to this Earth once you've extracted it from the moon's surface. The percentage of helium that we typically call the base for economic is 0.3%. This turns out to be, it was a number created in the 70s or 80s, and it's purely arbitrary and it's made up. There's some, like Qatar is extracting 0.04% helium, I believe, from the natural gas, but the amount of volumes of natural gas they move every day make it an economic adventure. What also is critical is all that you see on the screen, just a typical an oil and gas project. Clays are a problem more in production than anything to do with the helium, same with water chemistry. But pretty much you look for it the same way you'd look for natural gas or oil. There's the characteristics of HE reservoirs. Now this slides from last fall, but essentially there is a hydrogen rich reservoir that holds helium, but we're not really understanding those as much. But mostly Most helium is made from, comes out of natural gas, but also carbon dioxide and nitrogen are producing helium. And especially in southeast Saskatchewan, most of the helium is from nitrogen-rich reservoirs. There's no methane, a little bit of CO2 in them. And then the high helium, we have lower high helium. The high helium reservoirs tend to be very small. If you get 7 or 8, 10%, they have limited extent and their life is very short. But people love to see those big numbers, even though the reserve estimates are typically very small compared to what you would find at a lower number, like 1 or 2%, 1.5%. They're more laterally extensive. This is the gas composition of several fields, and as you can see, they typically are one or the other in terms of it's either the host gas is predominantly methane or predominantly nitrogen or predominantly carbon dioxide. There are some mix. If you have a mixed reservoir gas, it actually adds to the processing costs and problems. This is a map of the US showing where most of the helium is being extracted. The blue circles are areas that have potential. The Ruddard area, which I did worked on briefly before, was taken over by another company. I think it's Helios or something like that. And they've got Ruddard going, and hopefully they'll do very well with it. It's got helium both in the Cambrian sands as well as a little bit up into the Ordovician rocks. The east part of the country is devoid of any real helium exploration except at Bald Eagle, where a TSX company is presently expanding drilling and stuff. It's in a part of the rift systems that's igneous rocks. It's also seemingly has low pressure and it's drawn down very quickly. And then other areas like Kentucky, where it says Rome, those are areas I'm pursuing because there's that's like southeast Saskatchewan with nitrogen. Southwestern Ontario, that will have natural gas, but there's helium there. And then in the central part of the Michigan, presents a lot of opportunity because it's also a rift system like the Rome or other areas. So you have a lot of areas, but mainly down in the southwest part of the country, and Texas is where most of the helium has come from. And this is the active areas in helium, and you can see that the Minnesota one is very active. It's doubtful that it will go into production for another year or so, and the data coming from there is seemingly very limited, and what they say is usually can't be confirmed. Sweetwater Arch is starting to get a little activity. Southeast Saskatchewan, like I said, in Southwest Alberta is very active. Harley Dome, where we have drilled a well next to it about 12 miles away. And we think we have a helium zone. It's actually going to be tested tomorrow. So I'll know more about that. And then the Holbrook is an old area. Also, I'm active down there in the Pinta Dome. So there's a lot of good areas that can keep going back to. The Holbrook Basin, though, has a lot of teaser results, stuff where you can complete wells, but then they don't make helium after a few days. So there's a lot of risk in terms of helium at times, and you have to have a good team to reduce that risk. This is just a typical model. The helium migrates upwards from the mantle of crust, goes through the sedimentary section along faults, and then accumulates in various structures. And this is you can see Harley Dome up here. This is an area where I'd be working, and these are some of the gas wells that have been drilled. This is where various plants are. There's actually more than this, but it's very hard to find out where a plant is because helium industry is very opaque, not transparent like the oil and gas industry is, but there's mainly all the plants are in the West. This is our largest field in the country right now, Big Piney LaBarge. It's actually expanding down in this area by a company called Blue Star, I believe, which should go online in about a year and a half. But basically, this is a CO2 field, making about 0.5% of helium. And all that CO2 is used in eastern Wyoming for EOR. So that's the best way to get rid of the CO2. Otherwise, you'd have a problem getting the helium out of this field because you'd have to dispose of the CO2. Excuse me. Now, this is the big concern right now, North and South Pars. It's also got some other names that the media is using, but basically it's the field off of Cutter. This is what made Cutter such an economic powerhouse over the past few years. But you can see it's on a big arch. and that arch just has the largest gas field in the world. It's got some oil in it, but essentially the Iranian part is up here. And right now, this field is shut down or partially shut down. But you can see it has 1,800 TCF of gas with 0.04% of helium, which is hundreds of BCF of helium. This is another big field, or two big areas. This is the Russian area. There are two other plants. Well, all of their gas goes to these facilities, and they separate the helium out there. So we don't have much information on the fields and that sort of thing. This is in Algeria. This field is somewhat in decline, but there's other fields that are coming on with helium out of Algeria, and this is also on an arch. So arches are big things for helium production. Texas Panhandle, this is the field that started it all, or most of it, and this is in serious decline, but it's a huge field. It's made 400 BCF of helium, maybe if not more. It's very shallow. The reservoir is under pressure, so the helium doesn't get out through the seal. But I'm sure a lot of people are familiar with this field because um, it's been producing for decades. This is this Bow Island South Swift Current play. Some of the local operators have different names that they help promote, but essentially it's in this area, and this is an area where there's 5.5% of helium. It's Cambrian sands. This is an arch area or edge of basin area. So it's another way to look at these plays is that if you're on an arch or on the flank of a basin, that's where how to focus. And then this is just some of the promo stuff that comes out of these companies up there. Royal Helium is going out of business. Actually, it's in bankruptcy. Global Helium, I think they changed their name, but regardless, you can see the small structures compared to what we saw at LaBarge or Cutter. And they'll get one or two wells in this, maybe three, four. But essentially, the reserves are limited because of aerial extent. This is the Holbrook Basin. We had Desert Mountain here for a while, and now they moved to West Texas where they had some helium. Then they've moved back, but they're not doing helium anymore. The Pinta Dome has been around since the 60s, made quite a bit of helium at 800 feet. Essentially, though, this basin is full of helium. This is the St. John's structure. The helium is now it actually is declining. It's a 33 TCF gas field with 1% helium. Now it's less than that. And it hasn't produced for very long. Another big play that had a lot of hype, but finally the operators have gotten going is the Pishibaw uplift. It lies between the Raton and the Denver Basin. And basically the Lions here, which is the Model Dome, which has been around for decades too, they started drilling these little structures in the Lions. They have fresh water with them. The pressure is like 20 psi, just above surface pressure. So the flow rates are very low, but the gas could be anywhere from 2% to 8 or 9% helium. So it makes money because the wells are very cheap. This Bald Eagle field up here that's being operated by Pulsar was an accident by a mining company, ran into helium while looking for nickel. Someone at the USGS told the people who started Pulsar about it, and subsequently they've been up here and very active. And they found the first well they put down, actually the first two were severely under pressure because the well that the nickel company found flowed for 4 days before they plugged it. But it's typical of what's going on with a lot of these high-end percentage helium plays is that the pressure is somewhat lower or very low compared to a normal play at 1 or 2%. But essentially all along the rift system is areas that you could start looking for helium. Over in this area where it says A, H, and G, that's where a hydrogen play is, and they're finding good helium there, but the flow rates are just terrible. And this is just some more information that I brought up on the Bald Eagle intrusion. And like I said, this play won't be probably producing for another year or so. They're also going to try to sell the CO2 as food grade. The problem with that is you have to have a market nearby, and they're not exactly near any big cities, but I hope they get it done. And then Tanzania is another exciting play, except the problem is the helium's breaking out of the water. So you have to move a lot of water from this volcanic region. And so that's another issue is disposing of the water. I believe it's somewhat fresh, so I don't think they'll have a problem getting rid of it. But relying on moving thousands of barrels of water a day, that does lead to operational issues. Now, this is the area where I just may have had a discovery. It's not, this is Harley Dome. Um, and if you go up here to Cisco Springs, it's right up here. We had a structure that, let's see if the next slide, yeah. Next slide, you can see the structure. We had all sorts of geochemistry, various aeromagnetics and that sort of thing. This is the result, HE here, but actually the zone we're looking at now is in the Dakota above it. And hopefully that's going to flow. It gave us a tremendous helium kick at shallower depths than the Entrada. The Entrada, we just couldn't get anything out of. It may have been damaged by the 10-pound mud, but regardless, it just didn't look that encouraging. And so that's hopefully a discovery. If not, well, it was a good test. Then in Australia, what we're seeing here is this is all hydrogen plays. And subsequently, they've been drilling wells all through here, and they're still drilling wells, and they're running into the same problem. All hydrogen explorers are, the reservoirs are extremely under pressure. Also, they're now that we're analyzing for hydrogen, it seems to be everywhere in the gas in the rock column. And some of that hydrogen is actually generated by the bit hitting um, iron-rich rocks and releasing hydrogen. So there's a lot of problems, and subsequently, they're not flowing to surface, which means it's going to be very difficult to find a hydrogen reservoir that can go 10 million a day. And that's the goal. And right now, there's a growing amount of realization is that maybe this hydrogen play is subsurface hydrogen is not going to work. And then the southern mid-continent, this also is a hydrogen area. I mentioned it briefly earlier. And there is quite a bit of helium results along here. No one's really focused on that, but this is where they've been focusing for hydrogen. And there's several wells drilled, all with the same results of nice shows, bubbling out of water, but no flow rates. This is the Virginia gas field in South Africa. This is sort of really cool. You have uranium in the conglomerate that produces gold at depth, and that's been generating helium for millennial because this is a big crater, largest in the world. It's called the let's see if it's on here. I never can pronounce it. Anyway, it's the Witwatersrand complex, but the crater begins with a V. And subsequently, it created this massive resource area. And now they're getting helium out of this. So the helium comes up to the Karoo sand and then gets trapped. And it's just biogenic methane that's coming with the helium. So they're two independent things. So in summary, helium is a critical element for modern society. Most of the helium is produced by the US, Qatar, Algeria, and Russia, but that is changing. The central part of the mid-continent and central and southern Rockies is the area of US production, and in Canada, southeast Alberta and southwest Saskatchewan. Finding these reserves is difficult. It can sometimes seems like it's easy, but helium is just this elusive element. But sometimes once you find it, it can be very lucrative. Recovering helium from the host gram stream can be expensive. That's the biggest stumbling block for most people. Those processing facilities go for anywhere from $3 million to $6 million. So you have to make sure you have a good helium reservoir before you order that plant. Purchasers are limited to 6 companies, but you can sell it to end users yourself. It just takes a little bit more work. And helium is a uniquely financial regarding opportunity. Helium prices are now going up because Qatar's out, and with Russia being banned and trying to sell through China, that's another problem because Russians are delivering very impure helium, from what I understand. That has to be reprocessed that costs more money. But regardless, thank you for having me today, and I hope you learned something.
Yeah, that was great. And so just to recap, if you have a gas discovery and you have some helium in it, then you essentially you have to use a cryogenic process to
There's
um,
2 processes.
for the
Cryogenic is correct. Pressure swing absorption is the other, and that's the cheaper one.
okay.
I'm working with a Chinese company, and they're asking me to help them sell cryogenic units. And based on the initial work, their cryogenic units are cheaper than PSAs or pressure swing absorptions, but we'll see. We don't think the tariffs apply to their equipment, but I haven't confirmed that with the U.S. government yet. But if you can do cryogenic and in a liquid
Hmm.
form, you can move 5 times amount as much helium in a trail. They're all moved by trailers than
Hmm.
you would in the gas form. So there's an advantage to cryogenic uh, in the liquid form. If you just use cryogenic to drop it out in the gas form, there's no real advantage unless the price is the same or cheaper than a PSA. So,
Hmm.
but the price of things are changing all the time, and the Chinese are very good at making things far cheaper than us, sort of like the way the US was in the late 1800s with the rest of the world. So, if I can get a cryogenic unit that also has a liquefier for 3 million, I won't buy a PSA for 3 million because then my gas from there is only 98% pure, whereas with a cryogenic unit, it's 99, 99, 99. So
It
it's
does
it's
that
just
work? Then also, isn't there sometimes with CO2 a CO2 issue?
yeah, well, it depends what your host gas is. If you
Right.
have nitrogen, it's great, but the problem with nitrogen is if you don't have any methane, is you have no way, you don't have any cheap power. But
Hmm.
if you have gas that's with methane, obviously you can convert that to power to run the equipment, which saves you
Right.
money. With CO2, the biggest thing is not only do you have an inability to generate power, but then the CO2, is an environmental concern. And
Hmm.
the people with CO2 are trying to do things like go to food grade. The Labarge field sends it for EOR, which Exxon makes a lot of money every year selling that. They've got a very big field. They produce, I think it's 30% of the helium in the country or 20%. So it's a very successful relationship between those two, that element and carbon dioxide. So it just depends on what you run into. I prefer to run into gas wells that have methane in them, but there's areas like in Kentucky where they'll have nitrogen, but there's shallow oil and gas zones that if you run into, you can provide your own power that way.
Wow, that's interesting.
Yeah, there'll be a quiz.
Well, and I think, it's co-produced natural gas. I mean, it seems like a perfect solution, except that you've got to get a compressor um, and then you have to do, so it's, anyway,
Well,
you have the separator I mean, it's good, but it's not necessarily as easy as it sounds. So I think that's
that's
the
correct.
thing. Right. So to me, that's the thing that's the big issue with a lot of these um, um, exploration and prospects or ventures is that one has to look at it with really open eyes to say what are the real operational issues.
Right. Well, that's the thing is that it's not like an oil and gas field where, let's say it's an oil well, you can get it online in 20, 30 days. And natural gas, if you're in a field, you connect pretty quickly, let's say in 20 or 30 days. But if you find a helium field, then you order the plant, you're going to be waiting 9 months to 2 years to get the plant delivered. So that's the real downside. But the thing is when you get $400 an MCF for your gas, um, if you even got an average size field or one of these smaller fields and you have good reserves like the small fields in southwestern Saskatchewan are making good money. The problem with that play up there is the companies have got seriously into debt or raised so much money, it's going to be very hard for their stock price to go up. But at the same point, um, there's companies that will come in behind them and sort of learn from things they just didn't do right. But there's a lot of companies that raise money around 2020 to 2023. I'd say half of them went out of business is because they underrepresented what the sort of monies they need and how long it would take. And that's typical in the small junior market or small OTC market with companies. They always try to raise a couple million when they really need $20 million. So it's just and then private companies, uh, I see some of those doing a lot better because they don't have to uh, talk to the stock market all the time.
Right.
You
Yeah.
know,
No, that's a kind of, so this becomes an issue of not just the resource, but also the technology and the
right,
financing of the technology. So it's really fascinating, and it's a good idea, good idea for these startups to have an exit plan that's early rather than thinking that they can conquer it all.
right, right. So, but at the same point, helium demand is going to climb by, it's climbing, I've heard anywhere from 5% or to 12% a year. And they expect with AI, it's going to rapidly climb higher. It's used a lot in space uh, for rockets and that sort of thing. So, and we see SpaceX continually increasing the amount of rockets they're putting into outer space. So, helium is only going to get more expensive unless there's a lot of drilling and a lot of way to make it cheaper to get out of the ground.
Well, looks to me like when you see some moon mining, which
Yeah.
is kind of problematic because how do you do it? And do
Well,
you
how do you
just
get it
like,
home?
well, yeah, I mean, do you kind of blow up a piece of the moon and bring it to within our orbit and use it like a satellite and just mine it from there? And then what does that do to the moon itself?
Right. I don't know.
Anyway.
I, the one thing you could look at, I guess, is they could put a refueling station up and circling the Earth and deliver the helium that way to spaceships. But regardless, I think it's very far away, at least in our lifetime, that the moon will be mined efficiently. But I've been wrong before.
Well, it would be wonderful to explore that in a sci-fi.
Right. Yeah, go see the Rockwell film. It was actually cute.
Okay, yeah, I will.
Yeah.
Well, thanks, Steve. So everyone, you've been listening to Dr. Stephen Tedesco,
Thank you
and
all.
in the slide you see the picture of the cover of the first edition of his book, and the second edition will be out soon. So we're
Yep.
really privileged, and thank you.
Thank you. That was good.
Okay, just a second.